Hi, my name is Arish Virani and this is my fourth lab, Oscillations. As for an introduction, our purpose is to model and validate the 2D motion of a mass on a vertical spring under gravity using tracker XY data. Examine the motion of a spring mass system in which the mass swings in an arc while also oscillating on the spring. Overlay the model with measured trajectories and compute delta K, delta UG, delta US, and delta E, also known as change in kinetic energy, change in gravitational potential energy, change in spring potential energy, and change in energy to test the energy principle. Estimate oscillation periods independently from X and Y and compare the results. So brief preview, the mass spring motion is captured by gravity and Hooke's law. The model X and Y closely follow the tracker data in frequency with a small expected phase offset and minor late time amplitude drift. Calibration are non-ideal effects. Energy plots show delta K, delta UG, and delta US trading off while delta E approximates to 0, indicating total energy is conserved in the model. Periods extracted independently from X and Y agree within a few percent, confirming a single dominant oscillation frequency in both directions. So our physics principles and formulas, we use the Newton's second law, the momentum principle. We treat the mass as a point particle. The net force equals the time rate of change of momentum. We update velocity or position from the net force. Gravity and Hooke's law model, the spring pulls along its axis towards the anchor. Define the geometry from the anchor to the mass, extension S as length minus relaxed length. Energies and energy principle, kinetic, gravitational, and spring potential energies trade off in an ideal model, leading to the total energy change being approximately 0. Period expectation for small oscillations of a vertical spring, gravity only shifts the equilibrium. The oscillation period is T is equal to 2 pi squared m upon k. Hence, X and Y should show the same fundamental period up to small phase or amplitude differences. So our observed model uses the tracker software. Our system is the spring, earth, and mass, and our surroundings are damping sources like air resistance that we assume is negligible for the model. Our models and procedure are as follows. I model the mass as a point attached to a light ideal spring that is fixed to the board and free to move in the plane. The only forces included are gravity downward and the springs pull along its own axis. The parameters, mass, spring constant, and relaxed length. The anchor is fixed, and I neglect air drag and the spring's mass. I track kinetic, gravitational, and spring energies and check that their sum remains nearly constant. In tracker, I calibrated length and frame rate, marked the mass throughout the video, and exported only the X and Y columns to a CSV with no headers. In GlowScript, I loaded that file, set the given parameters, started the model at the measured initial position, and computed the motion over the same time window while drawing the spring and ball. I overlaid the predicted and measured X and Y and plotted the energy changes to test the energy principle. Finally, I estimated the oscillation period twice, once from peaks in X and once from peaks in Y. I averaged several cycles for each and compared the two estimates while noting likely discrepancies from calibration noise, manual marking, camera tilt, and small real-world damping. So the model is through the GlowScript computation. Our initial conditions are as follow. The ball starts at minus 0.12, minus 0.630 meters, and our mass is 0.402 kilograms, and our initial velocity is 0. Gravity is G is equal to 9.8 meters per second squared. The spring constant is K is equal to 6.83 newtons per meter. The relaxed length is 0.123 meters, and the time step delta T is 1 upon 210 seconds. The spring's fixed end is at the origin. So I define L as the vector from the anchor to the ball, take L hat as its unit direction, and compute the extension S is equal to magnitude of L minus L naught. With that, I calculate the energies kinetic, K is equal to half mv squared, gravitational, UG is equal to mgy, and spring energy, which is US is equal to half ks squared. I also set the helix axis to L, so the drawn spring tracks the ball. Each step, I first snapshot the current energies for comparison, then I compute the forces. Gravity is straight down, Fg is equal to 0, minus mg, 0, and the spring pulls back along the spring, Fs is equal to minus ks L hat. Adding them gives the net force. I apply Newton's second law to update the velocity and then the position using the net force and delta T. After moving the ball, I recompute L hat S, update the spring graphic, and append a point to the trail. I recalculate K, UG, US, and the total energy, which is equal to the kinetic energy plus gravitational potential energy plus the spring potential energy, and plot the changes in each. In the results, the red gravitational and green spring energies trade off. The blue kinetic spikes near equilibrium crossings, and the orange delta E line stays 0, which can be shown in the next few slides with our graphs. And the data overlay, I overlay tracker measurements by plotting one video point about every 20 simulation steps. That lets us compare the model's X and Y directly with the recorded motion. As you can see here are the final results with the X position and the Y position against time, and the change in energy with the time, along with the color coding for delta K, delta U grav, delta E spring, and delta E. So assumptions and overall analysis. I model the ball as a point mass attached to an ideal massless spring fixed to the board with motions confined to a plane. The only interactions included are gravity with Earth treated as part of the system and the spring. The anchor is rigid. Parameters M, K, and relaxed length come from the pre-lecture, and the simulation advances with a constant time step using the measured initial position. The model reproduces the observed oscillatory pattern in both X and Y over the full run, matching the dominant frequency and behavior seen in the tracker data. When plotted together, the predicted and measured positions align closely cycle to cycle. The agreement is strongest in the central position of the motion with minor late time amplitude differences that remain small compared to the overall oscillation. The computed kinetic, gravitational, and spring energies trade off as expected, and the total remains essentially steady throughout, indicating that the internal counting of the model is self-consistent. No free parameters were tuned into the data beyond the given MK and relaxed length. The CSV was used to set the starting position and for comparison only, which supports the model's predictive validity. Sources of discrepancy or error, I treated air resistance, friction, and external conditions, room, air, floor temperature as negligible. Ignoring these can slightly change amplitude and period. The simulation advances in discrete time steps. Any finite step size introduces small errors, and large steps create larger drift. Clicking the marker and tracker by hand adds pixel noise and small time misalignments. So what does it mean? Part 1, for your model system, is the energy principle satisfied? Judge your answers by discussing briefly your plots of energy changes. Yes, our model's total energy change stays approximately 0. The change in kinetic energy, change in gravitational potential, and change in spring potential energy curves trade off, while the orange change in energy line sits at 0 for the whole run, which is the signature of a conservative spring gravity system. Part 2 of what does it mean is using the data you obtained in tracker, make two separate estimates of oscillation periods. First, by estimating the period of oscillation from the X position data, and second by estimating the period of oscillation from the y position data. Compare the two estimates and discuss. I estimate the period twice from my experimental red curves by timing several peak-to-peak intervals and averaging. The x peak times are 1.235, 4.559, 6.173, 7.883, and 9.497, which brings us to 1.65 seconds for x, and y peak times are 1.995, 3.514, 5.034, 6.553, and 8.073, which brings our y to 1.52 seconds. And the difference between the two is 0.13 seconds. The x and y periods are close, both near the theoretical 2 pi square root m upon k, which is equal to 1.52 seconds in our case, as expected for small oscillations where gravity shifts equilibrium but does not change t. The slightly longer tx is consistent with detection or sampling effects. A missed early x peak and small in camera tilt makes x peaks a bit harder to pick, and minor damping and amplitude asymmetry in x. So our conclusion: the hanging mass behaves like a nearly ideal spring gravity oscillator. Our model matches the tracker motion in x and y and keeps total energy constant, approximately constant, with delta k trading off against delta ug and delta us. Periods from data agree with each other and with the 2 pi squared m upon k formula. Small phase or amplitude gaps are consistent with light damping, and minor calibration or alignment error. All of this can be seen in our change in energy versus time graph. Thank you.